Hi everyone, we're solving this physics paper 5 today. This is 9702 paper 5-1 in the October-November 2023 series, and the time is 1 hour 15 minutes. So before we begin, let's take a look at the threshold. Also guys, if you like the videos, please remember to subscribe to the channel and hit the notification button so that you don't miss any videos. And also if you guys require more help, you have access to my Patreon. I'll give a link in the description where there are 3 tiers, one for support, general support, and the other one for solve papers, notes, and requests for my future videos. Here you get access to help uh, over text with me, as well as access to all my solve papers from 2002 to 2023 for physics, chemistry, bio paper 1, 2, 4, and 5, and math P1, P3, M1, and S1, as well as access to notes for AS and A2 physics and chemistry. And for the ultimate learning experience, you actually get access to 1 or 2 video calls with me a month where we can go through your personal problems, right? Okay, so let's begin. So this is the threshold. So for paper 5-1, I have plans to solve all the paper 5 as well, paper 5s as well as for 1 and 2 soon. Hopefully before the May June 2023 session. Let's see how it goes. 2024 session, I mean. So for paper component 5-1, out of 30, A was at 23, B at 21, C at 18, D at 14, and E at 11. Okay, so out of 30, A was at 23, B was at 21, C was at 18, D was at 14, and E was at 11. So A star should be at around maybe 2-3 marks more than this, 25 or 26 probably. That is how it looks like. So yeah, let's start with question 1. I actually have this solved, so we're going to be done pretty soon, like 34 minutes. So we have 2 coils C and D which are placed with their axis on a straight line. So this particular question is very similar to May June 23 variant 5.2. Let me show you a picture. So almost the same. It's almost the same actually. Uh, I don't know if I have this solved in my channel yet. Uh, if I don't, I'll solve it soon. But this is very similar. It's also a question about induction. So let's take a look at this. A resistor of resistance R is connected in series with coil C. A changing magnetic flux of frequency F in coil C causes an EMF to be induced across the terminals of coil D. It is suggested that E is related to F by the relationship E is equal to Pf to the power Q times V divided by R, where V is the potential difference across the resistor and coil C, and P and Q are constants. Plan a lab experiment to test the relationship between E and F, and draw a diagram showing the arrangement of your equipment. Okay. Now, first things first, the first 2 marks, defining the problem. We need to state the dependent and independent variable. Always think of it chronologically. Okay, the relationship is between E and F, right? So think about it, which one comes first? Does the frequency in coil C come first or the induced EMF? Clearly the frequency will come first, followed by the induced EMF. So the one that comes first will always be the independent variable. So the frequency in coil C is the independent variable and the induced EMF in coil D is the dependent variable. Okay, that's the first point. Next, moving on to the second marking point, things we have to keep constant. Okay, so E and F are variables, so they can't be kept constant. P and Q are already mentioned in the question, so they can't be they are already mentioned as constants, so we don't need to repeat that same point. Now we end up with V and R. Those are the only 2 letters left in the equation, where V is the voltage in coil C and R is the resistance of resistor R. So we will say that keep R constant and keep V constant. That should probably be it. Okay. Next, moving on to methods of data collection. How will we find out the variables, these data? How will we find these out? So the induced EMF can actually be found out using 2 ways. You can either use an AC voltmeter connected across coil D. Always connect the voltmeter across the coil where the voltage will be induced, right? Or a better option is using a CRO. Okay, So what is the benefit of a CRO? You get access to two more points. So you could talk about how you can find out the voltage, from the Y gain, right? And how to find out frequency. Basically, to do that, you have two options. You could either connect a signal generator to coil C, which produces the alternating supply, and you could read off the frequency from the signal generator. That is one route. Okay, so in the diagram, you mainly need to draw the circuit like this. The coils need to be along one line. You need to draw a voltmeter across coil D, and you need to draw a signal generator across coil C or an AC power supply. Now, I will tell you the benefits of an AC power supply over the signal generator. If you use an AC power supply, you can also use an oscilloscope along with it. And using that oscilloscope, you can actually find out the time period using time base times the horizontal distance followed by frequency is equal to 1 by time period. You get access to extra points basically if you use ACRO. So that is the logic, okay? So let's begin. So take a look at the red points first. This is what I talked about already. F is the independent variable and E is the dependent variable according to chronological order. Or you could say vary F and measure E. It has the same meaning. And I already told you my thought process behind keeping R and V constant. This red part is the is defining the problem. All right. Next, this is the diagram essentially. So what things are optional here? These things, the ammeter, these are optional basically. This is what you had to draw, okay, to score marks in the diagram. They had to be labeled, kept side by side along one line. We needed a workable circuit of coil D along with an oscilloscope or a voltmeter. An oscilloscope or a voltmeter. And yeah, we needed that. Yeah, that's all. And on the left hand side, we either needed an AC power supply or a signal generator, right? Okay, so that's that. Now these points are extra. I'll tell you why. So you can draw this. You can pause here and draw the diagram. So I'll tell you what these are for again. The oscilloscope connected to coil D is to measure the induced EMF, capital E. The AC power supply across coil C is used to create a changing magnetic flux, changing current. And the oscilloscope has to be connected parallel to both R and C. You could draw it this way or you could draw it this way. This is also fine. Same thing. You get marks for both. It has to be connected parallel to both the coil C and R because we are measuring the EMF of that circuit, the total voltage. Okay, where V is the potential difference across the resistor and coil C. The potential difference across resistor and coil C. That's why it has to be connected parallel to both, okay? So yeah, that's that. You get 3 marks here. You get 3 marks over here. And for the 4th mark, you just have to say either if you use a signal generator here, you have to say read F off from the signal generator, or if you use an oscilloscope like me, say use the oscilloscope to determine F. Now we go into additional details. In this section, the one with the diagram, it's called methods of data collection. You have 4 marks, all right? Now moving on to the next part, we have additional details, which has a total of 10 marks, but you can score a maximum of 6 from those 10, okay? So what are these? The ones I've already told you, like to find out time period, you can use time base times horizontal distance from the oscilloscope, the one on the left, and then frequency is equal to 1 by time period. So that's one. Next, to find out voltage, the induced EMF, the voltage, E or V, you can simply go for using the oscilloscope. Y gain times the vertical distance, you've learned this in AS. If this is a waveform, right? You know that the vertical distance times the Y base gives you the Y gain gives you voltage, and the horizontal distance times the time base actually gives you the time period. Okay. Now, some additional details, okay? So we know that this is an experiment of magnetic flux linkage. So we know that the induced EMF is equal to n del phi by time. So we need to keep the number of turns constant, right? So that is also another additional detail. And also, Since R is part of the equation, you need to say how you're going to measure that. We said how we're going to measure E and V. We said how we're going to measure F, but we didn't talk about R. So R is a resistor. So there are two ways to do it. Firstly, you could talk about an ohm meter. You could say use an ohm meter and then connect an ohm meter in series with the resistor. That is one route. This is how you draw an ohm meter. You have to connect it in series with the resistor. That is one route. But since the ohm meter is not actually in our, in the circuit symbol list, I would not prefer that, honestly. That is why I always opt for the simpler method. Connect an ammeter in series with the circuit and a voltmeter in parallel with the resistor, and then just simply say R is equal to the potential difference across R divided by the current in R. R is equal to V by I. That is one point for writing this down. And there is another point for the correct circuit symbols, like the ammeter and the voltmeter. That's another additional detail. So 2 marks over there, right? And then 2 marks for time period and voltage. Keeping the number of turns constant is another point. And the safety precaution here is, since the coils are going to be really hot, right, we have to use heat resistant gloves to handle the hot coil. Always link the safety precaution with the hazard. The hazard here is the hot coil, and the safety precaution is using heat resistant gloves. So that's 6 out of 6. Okay. But I'm going to teach you the other 4 as well. So what else do we have? Okay, what else do we have? So the distance between coil C and coil D need to be kept constant, or else it will affect induction, right? So that needs to be kept the same. Okay. And how will we do that? But we can fix them or clamp them to the table. We can clamp the coils. And yeah, to reduce error, we always prefer large values. So what can we do to reduce error? Basically, to increase the value of the induced EMF, we can use a larger voltage in coil C, or we could increase the number of turns, or we could bring the coils closer. So just mention any method, or we could use an iron core, or we could decrease resistance. All of these help in increasing the value of the induced EMF. Okay, so that's our goal, to reduce error. Use larger values, find out a larger value of the dependent variable to reduce the percentage error. Okay, and sadly there was no point for repetition in this experiment, which is pretty common in other variants. I don't know why. Maybe there were too many points already. And for analysis, right, what do we need to do? We need to break this down, and since E is the dependent variable, it should be on the left side of the equation. And if you see any powers, automatically default to log or ln. Okay, so this is what I did. Log E, right? Log E is equal to log Pf to the power q v by r. So log E is equal to log Pf to the power q v minus log r. Log A by B is equal to log A minus log B, right? Next, log E is equal to log P plus log F to the power Q plus log V minus log R. I separate log F since it's the independent variable. Finally, we end up with log E is equal to Q times log F plus log PV by R. Okay? So the analysis will be like this. We need to plot, we need just cut the, we need to just say plot a graph, right? Plot a graph of log E against log F. Okay, and the relationship is valid if a straight line is obtained or produced that passes through the y-intercept of log PV by R. So this is usually part of analysis, but in this particular question, it's part of additional details. I'll tell you why. Because there are two constants in this experiment. So 1 mark for explaining how you are going to get the value of each constant. So since they take 2 marks, 1 mark each, that is why this point is actually part of the additional details. Okay. So one more over here. And finally, we have to say how we get Q and P. So Q is actually equal to the gradient, since you can see y is equal to mx plus c, like this, mx plus c. And the log PV by R is actually the y-intercept. So PV by R equals to 10 to the power y-intercept. And finally, P is equal to 10 to the power y-intercept times R by V. So that is it for this experiment. Pretty straightforward and good for understanding magnetic induction as a whole. And I would recommend doing Meijun 23 variant 5.2 if you haven't already. This is important for your exams. Okay, so moving on to question 2 then. A block of modeling clay of mass m is attached to a string as shown in figure 2.1. A pellet traveling at speed u enters the block and causes the block to move through a vertical distance h. The experiment is repeated for different values of m. It is suggested that h and m are related by this particular equation. Fine. Where g is the acceleration of free fall and z is a constant. A graph is plotted of root over 1 by h on the y-axis against m on the x-axis. Determine expressions for the gradient and y-intercept. Fine. So I want root 1 by h, so I'm going to root the whole equation. So root 1 by h is equal to root 2g times m plus z divided by uz. M plus z by uz had a whole square, now it's gone. Now my goal is root over 1 by h is on the y-axis, it is the dependent variable, so it will stay on the left hand side, and I'm just going to break down the right hand side. Okay, so on the right we have root over 2g times m by uz plus z by uz. We can get rid of the z's, and finally we end up with root over 1 by h is equal to, I'm keeping m separate since it's the independent variable, root 2g divided by uz plus root 2g by u. So root 2g by u is our y-intercept, and root 2g by uz is our gradient. Okay, so that's that. Moving on to the table then. So how to solve this table? Basically it's root over 1 by h and nothing was done to the units. Okay, so this is what you do: 1 divided by 21.0 and root over answer. Now about the significant figures, right? Since our data has 3SF, the answer can be given to 3SF or 4SF. That is the rule. Since the data is in 3SF, answer can be given to 3SF or 4SF. Okay, so I end up with 0.21822, so I can either give the answer as 0.218 or 0.21823, 3SF or 4SF. I obviously choose the easier path, the 3SF path, because it will be easier to plot the data. Now about the uncertainty, how to do it. So this is the general rule, right? Del root over 1 by h by root over 1 by h is equal to del h by h. But there's another additional detail here, the half. Okay, why do we have this? So this is due to the root over sign. Whenever we have a power, it will come to the front for uncertainty. Like if you had square, it would be 2 times del h by h. Since we have a root over, which actually refers to a power of half, it actually turns into half times del h by h. Now finally, we actually end up with this. After you solve this, half times, you know, these values over here, um, 0.2 and 21, 0.2 and 21, half times 0.2 by 21 times 0.21822. That's the value of, you know, the one we have here, essentially 0.218, and we end up with 0.001039. Fine. So I repeat the entire thing for all the other values and get these values. You can check if you want. I'll just stop here for a second. You can pause and check. Next, we move on to the graph, right? So we have to plot a graph of root over 1 by h against m. So I brought the values here. You can plot the graph first and then check with me. You can pause here. So I'll teach you the scaling. For example, 0.218 and 565, right? So 565, what does this mean? This is 500, this is 600, so this is 550, sorry. So 560, 570, 580, 590. So 565 should be in between 560 and 570. So this point over here, that's 565. Okay, so at 565 we have 0.218. So what is 0.218? This is 0.21, this is 0.22, 0.211, 212, 213, 214, 215, 216, 217, and 218. So each box is 0.001. So the eighth box is 0.218. At 0.218 it is 565. Okay, that's the point. And you have to use crosses, please. If you don't use crosses, they might deduct marks. Either dots or crosses, but you cannot circle the dots. Okay, no blobs are allowed. You cannot circle the dots. Okay, so if you guys want to check once, this is how the points are. I've labeled them for you. So 0.218, 0.565, that's the first one. Then we have 0.237 and 637. 0. At 637 we have 0.237, seventh box. Then 0.248 at 675. 675, 0.248, eighth box over here in the middle of 650 and 700. Then we have 0.262 at 723. 0.262 at 723, fine. Okay, you can actually round off 723 to 725, that is also fine, to the nearest spot, but you can also write like this. And then you have 0.282 at 790, 282, second box from 28, and 790, that's like two boxes before 800. And then 0.313 at 892, 0.313 at 892, 892, just after 890, or round off to 890. And 0.313, three boxes from 0.31. Yeah, so that is that. And for the error bars, what do you need to do? 0.218 plus minus 0.001, it's on the y-axis, so it will be vertical, right? So 0.219, it extends up to 0.219 and goes below to 0.217. So from 0.217 to 0.219. And for the last one, it's up to three boxes up and down, right? And for the third, fourth, and fifth one, it extends up to two boxes up and down. Okay, so that's that. Now for the line of best fit, right? You need to strike a balance. So I went for this: below the first point, above the second one, and then yeah, above the third one, kind of goes through the fourth one, then passes through the fifth one, and below the sixth one. It was really hard to do this one actually, but yeah, maybe it would be better if I drew something like this. Wait, if I change this, I lose the worst acceptable line. Wait, maybe something like this would have been better, like a bit below, somewhere here. Yeah, something like this, but it's fine, it's fine. This is all right. So to check your your line of best fit had to pass between 605 and 615 at 0.23 over here. You see these black lines that I've drawn over here? It had to pass through these black lines, and on top it had to pass through 845 and 855 at 0.30 here. Okay, if your line passes through these, you're good to go. And for the worst acceptable line, I chose to draw the shallowest line, so it passes through the lower bound of the highest point, and it passes through the upper bound of the point on the left. However, I actually tried to make it pass through this point. Okay, I tried to make it pass through this point, but then look, it does not pass through this error bar over here. As a result, whenever you try to draw it this way, always try to draw the connect the lower bound of one point and the upper bound of the other on the other side. But if it doesn't pass through all the error bars, check with your transparent scale first. Then you need to edit it a bit. Edit it so that it passes through all error bars. Okay, so I just edited a bit, like since I saw that it was here, I just brought it a bit closer until it touches the error bar. You see what I'm doing? Just touches the error bar over there, and then you are good to go. Okay, so that is your worst acceptable line. Please do label them as the line of best fit and worst acceptable line, not worst fit line, worst acceptable line. Okay, then please draw the dotted triangle. It is recommended. I always draw one, which goes for both lines. I take a triangle like that, and your points have to be at least 50% of the graph apart. Okay, and you can take the crosses. Okay, given that your line passes through them, but I always prefer taking other points. I don't know why. Makes it more realistic. Now then I chose the points. Here I have them written down. I write these down with a pencil. Like here I have at 565 70.22, 575.22. Okay, and on top, what do we have? 870.305. 870. At 870, the purple dotted line. 860, 870, we have 0.305 and 0.304. Okay, So using, and no powers on the side, so we don't need to do anything. So then I find out the gradient. I find these two values, 2.88 times 10 to the power minus 4. I'll check again, 0.305 minus 0.22 divided by 870 minus 575. That is 2.88 times 10 to the power minus 4. And the gradient of the worst acceptable line is 2.80 times 10 to the power minus 4. Then you simply subtract the values, right? And the difference is your uncertainty. So you can give this answer to 2 or 3 SF. I opted for 3. So that's 2.88 plus minus 0.08 times 10 to the power minus 4. That is your final gradient, okay? That's that. Okay, now moving on to the math. So determine the y-intercept of the line of base fit. Fine. So you go for y is equal to mx plus c. Then you input the values. Okay, you input the values. I actually, you can use a cross if your line passes through it, but I just use the values I use for the gradient, okay, and use the gradient that you just found out to find out the y-intercept using your values. I used 0.22 and 575 and my calculated gradient to find this. Then repeat the same process, but using your worst acceptable information now, the coordinates as well as the gradient, and then you get two values of c, y-intercept. Now subtract them as usual. Okay, subtract them as usual to find out the uncertainty in y-intercept, and that's that. I opted for a two significant figure answer here, 0.054 plus minus 0.006. That's the difference. Now you need to use your initial equation again, the one you actually simplified at the beginning. So then we are asked to find out the values of u and z with units. Okay, so this is a bit complicated. So u and z, so we clearly can't use gradient because it has two unknowns. We have to use root 2g by u. So root 2g by u is actually equal to the y-intercept. So u is actually equal to root 2g by y-intercept. So root 2g is root 2 times 981, and the y-intercept calculated one is 0.0544, and then we get a value of 814. Now what's the unit of this? Okay, so g had a unit of centimeter per second square, so root over that, and the y-intercept has a unit of centimeter to the power minus half. Okay, so if you do the working, above you have centimeter to the power half times second to the power minus 1 divided by centimeter to the power minus half. If you simplify things, you actually end up with centimeter to the power 1 and second to the power minus 1. So centimeters per second. You can honestly keep it like that, 814 centimeters per second, but it is recommended to give your answer to meters per second. Okay, so if you divide by 100, you actually end up with 8.14 meters per second. And for z, we go for root 2g by uz is equal to the gradient. So z is equal to root 2g divided by gradient times u. The gradient is 2.88 times 10 to the power minus 4, and u is 814. So I haven't converted to SI units here because everything is given in centimeters, so it helps to cancel things out. I actually end up with an answer of 188.88, which can be rounded off to 189 or 190, 2 or 3 SF. And for the unit, it's the same, root over centimeter per second square divided by, for u we have a unit of centimeter per second, and for the gradient we have a unit of centimeter to the power minus half divided by gram, which is centimeter to the power minus half into gram to the power minus 1. So after you do the root over, you end up with centimeter to the power half times second to the power minus 1. You can get rid of the second to the power minus 1 on the top and bottom, and you can bring the centimeter to the power minus half from the bottom to the top, and you end up with centimeter to the power 1 divided by centimeter times gram if you bring the 1 gram to the power minus 1 from bottom to top. So finally you can get rid of the centimeters and you end up with g only, so it is grams, 189 grams. And if you want to convert it to kg, the SI unit, you have to go for 0.189 divided by 1000. So yes, I will always recommend converting to SI units after you've done all the calculations, because in the mark scheme they said they want the SI units. Okay, and finally, for the percentage uncertainty of z, what does z depend on? 2g, which does not have uncertainty, and u and z. So sorry, Z depends on 2G, U, and gradient. So 2G does not have uncertainty. The gradient has uncertainty, which we found out in the first part, and U. U also has uncertainty. How did we find out U? U depends on 2G and y-intercept. So the uncertainty of U is completely dependent on the uncertainty of y-intercept. So Z actually depends on two things, gradient and U depends on y-intercept. So we can say it like this, Z actually depends on the gradient as well as the y-intercept. Because del y-intercept by y-intercept is equal to del U by U. Okay? So percentage uncertainty of Z is equal to del y-intercept by y-intercept plus del gradient by gradient times 100%. So I just used my values from here, 0.006 by 0.054 plus 0.08 from the top, 0.08 by 2.88 times 100%. I get an answer of 13.9%. Okay. Finally, the experiment is repeated. Now we have a value of h that is 25 centimeters. Find the value of mass. So I write down the main equation again. Root over 1 by 25 is equal to gradient 2.88 times 10 power minus 4 times m plus 0.0544. 1 by root over 1 by 25 is 1 by 5 is equal to this. And finally, I get a value of m is equal to 510 grams. Okay. That is all for now. I hope that helped you guys. I will plan to solve the other paper 5 soon, as well as paper 4, 1 and 2. So a quick shout out to my top tier patrons for the month who are subscribed to the highest tier, the Ultimate Learning Experience. We have Dewa and a new member joining this month, Prava. So if you want to be featured on the end page, please do consider supporting me on Patreon, where you get access to, the highest tier, where you have access to video meetings with me once or twice a month. Anyway, that's been it for the paper. If you have other questions, please do comment below. Or if I've made any mistakes, please do comment below. I will link the paper for October, November 2023, variant 5.2 up here, and the paper for May, June 2023, paper 5.1 down here, and the playlist for physics, paper 5 up here. And remember to subscribe to the channel. See you guys. Bye bye.